Webhooks explained in detail. This is the HTTP request that you did not send. It simply arrives. Over the next few minutes, we will build the receiving side properly, in real code, and look at the 4 things that go wrong after it lands.
Here is a real week. On Monday, a customer is charged twice. 1 order, 1 card, 1 click, 2 charges. On Tuesday, an order is marked as shipped before the row that created it even exists. On Wednesday, a stranger posts a fake payment to your server, and your server believes it. Nothing was wrong with the provider. Nothing was wrong with the network. The same 20 lines of your own code caused all 3, because that code assumed 3 things: that the message arrives once, that messages arrive in order, and that the message is really from them. Not one of those 3 is promised to you. Sending a webhook is easy. Everything hard about this subject is on the side that receives it.
So let us name the subject. This video is about webhooks, and mostly about the side that receives them. 3 things. First, what a webhook actually is. It is one HTTP post to a URL you registered. That is all of it. Second, what your endpoint must do and in what order. The order is the whole lesson. Third, the 4 ways it goes wrong: duplicates, wrong order, silence, and forgery. Now, some things this is not. It is not WebSockets. A WebSocket is one connection, held open, carrying traffic both ways. A webhook is one way and it holds nothing open. It is not a message broker either. Nobody is running a broker for you here. And it is not a protocol and not a library you have to install. Where does this bite? Any payment, any invoice, any refund that you did not start yourself. Any code push or build that triggers something. Any place where their system knows about a thing before yours does. One picture first, before any code. Imagine you are waiting for a parcel. You can do it 2 ways. On the left, you telephone the depot. Is it ready yet? No. You wait 10 seconds and you call again. No. Again. No. Almost every answer is worth nothing. You pay for every call anyway. And when the answer finally changes, you still hear about it up to 10 seconds late. The basket under that telephone is full of those answers. Now, the right side. You give the depot your address once. Then the driver comes to you the moment the parcel is ready. You sign a slip, and that slip carries a number. And look at the step. There are 2 identical parcels on it. That is not a mistake in the drawing. If your signature never gets back to the depot, the driver simply comes again tomorrow with the same parcel. Hold on to that picture. The signature is an HTTP 200. The number on the slip is the event ID. And the rest of this video is what happens when the signature gets lost.
Let us put a number on that left-hand side, quickly, because it is the reason the other direction exists at all. If you ask every 10 seconds, that is 8,640 requests a day just to watch one order. Now suppose that order really changes 10 times a day. Then about 0.1% of your calls carry any news. Everything else is the word no. And the 1 call that matters still arrives up to 10 seconds late. Watch 100 orders instead of 1, and you are making nearly 26 million requests a month, paid for on your side and on theirs, to learn almost nothing. So somebody had an obvious idea. Instead of you asking, let them call you.
Here is the whole system we are going to build. Their server, on the left, it sends a post when something happens. Then your endpoint. This is the box the video is about, and it is one ordinary route in the application you already have. Then a queue, which just holds the bytes until a worker is free. Then the worker, which does the slow part, the emails, the PDFs, the charges. And a database, which holds your orders and also one small row for every event you have already handled. 4 arrows, and every one of them is labeled. Their server and your endpoint talk in both directions because a post goes out and a status code comes back. And this whole video turns on what that status code means. Now notice what is missing. There is no arrow from your endpoint to the database. That absence is a rule, and we will earn it in about 2 minutes.
Let us kill the mystery first. This is their side, the whole sender. It takes your event and turns it into JSON bytes. It takes the current time. It hashes those bytes together with a secret that only the 2 of you know, and then it posts them with a few headers. That is it.
There is no webhook protocol, there is no webhook library. It is a post, a JSON body, and some headers, sent by an ordinary HTTP client. If that looks unremarkable to you, good. It is unremarkable. All of the difficulty is on the other end. Now your side. Here is the version almost everybody writes first. The event comes in, you read the order, you mark it paid, you send the receipt email, you render the invoice PDF, you reserve the stock in the warehouse, and then you return 200. Read those lines again. Every single one of them does something the business genuinely needs. The bug is not inside any of them. The bug is that all of them happen before you answer. Look at the numbers in the comments. 40 milliseconds, 60, nearly 2 seconds, 9.5 seconds for the PDF. Add them up, and this handler answers about 12.5 seconds after the request arrived.
And that is a problem because the sender is not going to wait that long. I ran this with a 5-second timeout on their side. Here is what each side saw. On your side, at 0 seconds, the post arrives and you start working. At 2 seconds, the email has gone out. At 5 seconds, you are still rendering the PDF. At 12.6 seconds, you return 200 to nobody because there is nothing on the other end of that connection anymore. On their side, at 5 seconds, timeout, no answer, marked as failed. For reference, GitHub documents 10 seconds here, and Stripe does not publish a number at all. Now the important part. They cannot tell the difference between a server that is slow and a server that is dead. From outside, both look exactly the same, silence. So they do the safe thing and send the event again while your first copy is still running. In my test, I ended up with 3 copies of one event running at the same moment. Nobody made a mistake here. The mistake is doing the work before answering.
So here is the fix, and it is a change of order, not a rewrite. Read the raw bytes of the body. Check the signature, which is 1 hash and takes microseconds. If it is not really them, refuse it. If it is, put those bytes on a queue and return 200 immediately. That is the entire handler. The work has not disappeared. It happens a moment later in a worker where nobody is holding a connection open waiting for it. I measured this version at about 1 millisecond instead of 12.5 seconds. And this is what 200 actually means. I have it. It does not mean I am done.
Same picture as before, with the boundary drawn on it. Your endpoint verifies and hands off. The queue is where the job becomes durable. The worker takes as long as it likes, and the endpoint still never touches the database. That is the rule I promised you. If the sender is still holding the connection open, you are not allowed to be doing work. There is one honest catch here, and it matters. The job has to be somewhere that survives a restart before you answer 200. If your queue only lives in your process memory, then your 200 was a lie. They will never send that event again, and it is gone. Let us look at those retries properly, because they are not a bug in somebody else's system. Why retry at all? Because no success code came back inside the timeout. Because a dead server and a slow server look identical from outside. Because giving up on the first attempt would silently lose real events and real money. So the only safe choice left is to send it again. But do not assume it happens. I read 2 sets of documentation this week, and they do the opposite thing. Stripe retries a failed delivery for up to 3 days with growing gaps between attempts. That growing gap is called exponential backoff. GitHub does not retry a failed delivery at all, not once. It says so in plain words in their documentation. So on GitHub, the retry loop is your code, or there is no retry loop. Both of them do give you a page where you can send a failed delivery again by hand. Go and read the page for the provider you actually use before you rely on a retry that may not exist. Now making the second delivery harmless. Here is the version everybody writes first, and it is wrong in a very specific way. Look up the event ID in a table of events you have already handled. If you find a row, stop. If you do not, do the work and then write the row. That reads perfectly. Now imagine 2 deliveries of the same event arriving at the same moment on 2 different workers. Both of them run the select. Neither has written its row yet, so both of them see nothing, and both of them decide that they are the first one. Both charge the customer. This shape has a name. It is called check then act, and it fails exactly when 2 retries land together, which is precisely the situation you wrote it for.
I ran that on a real Postgres database. 2 workers, 1 event ID, 200 trials. 200 times the same event was delivered twice at the same moment. 186 of those times, the Look It Up first version charged the customer twice. That is 93%. And with the version on the next slide, which is about 4 lines different, 0. So this is not a rare race that needs an unlucky day. It is the normal outcome when 2 deliveries of one event arrive together, which is exactly what a retry produces.
Here is the fix. Stop asking whether you have seen the event. Try to claim it instead. First, the table. 1 row per event, and the event ID is the primary key, which means the database will physically refuse a second row with the same ID. Now the handler. Open a transaction. Insert the event ID straight away before doing anything else. If that insert succeeds, you are the one who claimed it, so do the work. If it raises an integrity error, somebody else got there first, so return and do nothing at all. One small warning on that line. If you use an ORM, the driver error is usually wrapped, so catch the wrapped one or your accept block will never fire. There is no window between the check and the act anymore because there is no check. The constraint is the lock, and the database is the only thing in this picture that can actually hold one.
That code quietly raises a good question. What if the worker dies right after the insert but before the work? I tested all 3 orderings and the results are not symmetric. If you insert, commit, and then do the work, and you crash in between, the event is lost for good. Your own dedupe row tells the retry there is nothing to do. That is the worst one, and it is the one you get by accident. If you do the work first and insert afterwards, a crash in between means the retry does the work a second time. But if the insert and the work are in one transaction, a crash rolls back both of them, including the row, and the retry finds nothing and does the job properly. One transaction, exactly one effect. There is a limit to this. You cannot put charging a card or sending an email inside your database transaction. For those, use the other system's idempotency key. Most payment APIs accept one, and very often the event ID is a perfectly good value for it. Then a repeat becomes their problem to absorb, and they are built to absorb it.
Now the third bug from Wednesday, the stranger. Your endpoint is a public URL, so anyone on the internet can post to it. How do you know it is them? They sign it. They hash the body together with a secret that only the 2 of you know and send that hash in a header. You do the same hash and compare. Different? Reject it. 3 details here carry all the weight. First, it hashes the raw bytes. Second, the timestamp is inside the signed string, and we check that it is recent. Without that, a valid signature stays valid forever, and anybody who ever captured one request can send it again next year. Say that carefully, though. The window is not full replay protection. A copy sent 1 second later is still inside it. The window shrinks the danger from forever down to 5 minutes, and your event ID table closes the rest. Third, compare_digest, not 2 equal signs. I measured this one honestly. On a 64-character hash, the timing difference is real, but it is about half a nanosecond, far below ordinary network noise. Nobody is attacking you through it today. The standard library simply hands you the correct function for free, so take it. Now, the first of those 3 is where almost everybody loses a day.
They signed bytes, specific bytes, in a specific order with specific spacing. If you parse that JSON into a dictionary and then turn it back into a string in order to hash it, you are hashing a different string. There is a space after every colon now. Any indenting is gone. 1.10 comes back as 1.1. Accented letters get escaped. The trailing new line is gone. Every one of those changes the hash completely, and the signature check then fails on a request that was completely genuine, which is a spectacularly confusing thing to debug. And here is a correction, because I checked. Almost everybody says the problem is key order. In Python, it is not. Dictionaries keep their insertion order, so the keys come back exactly as they went in. The real culprits are spacing, escaping, and number formatting. And no combination of settings makes reserializing safe. I tried the tuned version too, and it scored worse. So in FastAPI, await request.body, which gives you bytes, and not await request.json. Verify the bytes, parse afterwards.
Second thing nobody promises you. Order. Remember Tuesday, the order marked shipped before it was created? Here is how that happens. They send the created event. It fails, so it goes into the retry queue. Meanwhile, the order gets updated, and they send the updated event, which arrives fine. Then the retry of the first one turns up, later, and overwrites the newer state with the older one. Retries reorder your stream, so do not trust arrival order. Trust a number that they put inside the body. Look at the where clause here. Update the row only where the stored version is lower than the one that just arrived. If an old event turns up late, the where clause matches nothing, and it is ignored, quietly and safely. I ran this with 8 processes throwing shuffled versions at the same row, and it always settles on the newest. There is one other correct answer, and it is simpler. Ignore the body and refetch the current state from their API. One extra request and completely immune to ordering. Both are fine. Trusting arrival order is not.
One more failure, and it is the one people forget. What if your endpoint is simply down for 2 hours? Normally, you answer 200. They mark it delivered, and nobody thinks about it again. If you do not answer, they move into retrying. Minutes, then hours, with the gaps growing. But retries do not last forever. Once the attempts are used up, they give up. And then nothing arrives. No error reaches you. The order is paid, and your system does not know. This is why every serious provider has a page listing failed deliveries with a resend button. Find out where yours is before you need it, not during the incident.
So here is the sentence to leave with. Design for at least once. Exactly once delivery is not on offer, and it is worth understanding why. They send the event, you commit it. Your 200 is lost on the way back. From where they are standing, that looks exactly like your server crashing before it did anything. The two worlds are identical from outside, so nothing they can build will tell them apart. To fix that, their send and your commit would have to be one single transaction, and they are never going to join a transaction with your database. So they have exactly 2 choices. Send once and risk losing it, or send again and risk repeating it. Everyone picks repeating, because that is the failure you can recover from. Now look at what you can have instead. At least once delivery, which they hand you, plus idempotent processing, which you build. The message may arrive once, twice, or 5 times, and the effect still happens exactly once. That is one unique key and one transaction. 2 traps on the way out. Answering 200 before doing the work is not a clever fix. It swaps duplicates for silent loss, and where money is involved, that is worse. And impossible delivery does not make duplicate rows unavoidable. That overcorrection is the expensive one. Nobody can promise the message arrives once. You can promise that it only counts once.
The whole subject as one chain, where each thing causes the next. You register one URL. That address is what the word hook names. They post to it, which is one ordinary HTTP request. Their server becomes the client, yours becomes the API. You must answer, and you answer with a fast 200. Verify, put it on a durable queue, return, and do the real work afterwards. A missing 200 causes retries, which are correct, because they cannot tell a slow server from a dead one. And retries are only safe if you have an event ID, inserted first under a unique key, inside the transaction that does the work. And underneath all of it, at least once delivery, plus idempotent processing on your side.
Thanks for watching. If that cleared something up, hit like and subscribe so the next one finds you.